Hi, AB students. This is the week 2 homework packet tutorial. In this packet, I basically took most of the problems and switched up the values. So I'm going to work through problems that are extremely similar to the ones on the actual packet. And then also, actually, some of the problems are identical. So if you're stuck on a problem, there's a chance I'm working through it. I'm going to work through it, and it's literally identical to the one that you are stuck on, because some of the problems they're like kind of hard to change. So I didn't change them. But anyway, let's get started. So the first problem, right, we see the limit of this function as x is going to infinity. Well, x is going to infinity. So the first thing we know is that it's an end behavior limit, right? Which you don't necessarily have to know by name, but can be helpful. So end behavior limit. Well, what do we know about end behavior limits? We really care about dominance. So our first step for these limits is always to basically identify the dominant terms in the numerator and denominator. And if it helps, you can rewrite the limit so it's only the dominant terms. So the limit is x going to infinity. In the numerator, the dominant term is obviously 10x because that's the only term. So it's going to be 10x. I'll circle it. In the denominator, the dominant term, well, we see x squared and then we see the 2x. Well, we know x squared is dominant over 2x. So I'm going to circle the x squared. But we have to remember that I can't just circle x squared. I also have to circle the negative symbol in front of it because we have to pay attention to the signs of the terms as well. So that's the other thing we paid attention to. So dominance and the signs. Those are the two things from end behavior limits. So I'll just write that, dominance and signs. So 10x over negative x squared, right? Okay, so the limit is x is approaching infinity. Well, 10x or negative x squared, which is more dominant? Well, negative x squared is obviously more dominant. So I'm going to say this is large, right? The denominator gets much larger, much faster. The 10x gets really small compared to the negative x squared. But also there's a negative symbol, right? So it's a negative, right? Because there's a negative x squared. So that negative 1 in the bottom, right, turns into, yeah, negative this. Well, what's something small? What is something small that's divided by something really, really big, like something really, really small? Well, that's 0. So it's 0. And then we also have a negative, so it's negative 0, but with this, it doesn't matter because negative 0 and 0 are the same thing. So we can just say it's 0. I will say, though, for example, if the limit was infinity and then we have a negative symbol attached to it, well, that's very different than positive infinity. Like negative infinity, we actually have to write the negative. So yeah. Moving on to the next problem, the limit as x approaches 5 from the left for x minus 4 divided by 25 minus x squared. I think this problem is kind of frustrating because our first instinct is like, oh, perfect, let us factor this. Like 25 minus x squared, that looks like it's just begging to be factored. So I can factor this. I'll just show you how I would factor this. So I'm going to factor out the negative 1. So it'd be x squared plus, oh, actually, it doesn't work. Yeah, so x squared minus 25. That's what would happen. So it would be equal to x minus 4 over negative x plus 5 times x minus 5. Right? So you're like, great, I factored it. Oh, I can cancel out. Oh, wait, no, I can't because the numerator is x minus 4 and the denominator is x minus 5. I can't cancel anything out, right? So what I'm going to do is I realize that when I plug in, right, I'm plugging in 5. I'm going to get if I plug in 5 in any of this, right, I plug in 5, I'm going to get 25 minus 5, negative 5 squared. So that's equal, sorry, that's equal to 25 minus 25 is over 0, right? And so I'm getting a 0 in the denominator. And even when I factor it out, I can't cancel anything out. So I'm still going to get 0 in the denominator. So what am I dealing with? I'm dealing with that asymptote limit. There's an asymptote there. And sometimes we have limits where it looks like there's an asymptote, like you plug it in and it looks like there's a 0, but we can factor it out and cancel it. In this case, we can't cancel it. We can't do it. So what are we going to do? Well, luckily, we're not asked to solve it directly. We're asked to basically going from 5 from the left. So what do we do for an asymptote limit? Let's plug in a number that's really, really close to 5 from the left. So let's say plug in negative 5.1, right? So I'm going to plug in negative 5.1. I get negative. So I'm going to get like x minus 4 over 25 minus x squared. Let's plug in negative 5.1 for x. So I'm going to get negative 5.1 minus 4 all over 25 minus negative 5.1 squared. I don't actually know what this is right now, but you could use a calculator, but I know the top is going to be like negative 9.1, right? And then the bottom is going to be 25 minus negative 5.1 squared is going to be slightly larger than 25. So it's going to be like 25 minus, let's say, 25.1. Let's say it's slightly larger than 25. So it's going to be negative 9.1 divided by negative 0.1. So it's going to be, the negatives cancel, so it's going to be positive. So this is going to go to, this asymptote, right, is going to go to positive infinity. So you could just say infinity. Remember, for an asymptote limit, right, let's say there's an asymptote here. When the limit approaches, it either goes to positive infinity or goes to negative infinity. There's no other option because it can't cross the asymptote. That's not allowed, right? That's not allowed. So it has to, like, once it hits it, it's like a wall. It's got to go either up or down. It can't do anything else. In this case, it's going up. It's going to up to positive infinity. So yeah, that is how we do this problem. Now, this is the limit as it goes to x approaches negative 6. Well, when I plug it in, right, let's see. Oh, I'm going to plug in negative 6 in the denominator plus 6. Oh, I'm getting 0 again. Oh, cool. Is it an asymptote limit? Well, let's try factoring first. So x. Oh, wow. Okay, I mistyped this. This was supposed to be what was this? This was, I designed this problem so you could factor it. Okay, let's just say I put 16 here. Wait, no, that doesn't make sense. Okay, oh yeah, let's put 12 here. So this is meant to be 12. This problem is meant for factoring. So if you are doing this problem, try factoring. So x plus 8x plus 12, so it's going to be x, right? I'm going to factor out the 12, factor it out, so it's going to be 2 times 6, right? Because 2 times 6 is 12, and then 2 plus 6 is 8. So yeah, over x plus 6. Okay, cool. So it's very evident this time. We can just factor it out. So it's not actually an asymptote limit because we're going to get x plus 2. So it's going to be the limit as x approaches negative 6 for x plus 2. Well, let's just plug it in. It's going to be negative 6 plus 2 is equal to negative 4. Cool. So I'll say this is a algebraic manipulation limit. So we can use algebra to solve for it. Great. Next, the graph of a function f is shown above. At which value of x does the two-sided limit exist, but is not equal to the value of the function? Okay, this is an interesting question. I also did not change this question at all because this question is hard to change. But at which value of x does the two-sided limit exist, but is not equal to the value of the function? If you're like if you know your definitions really well, you might notice that this is asking like the exact definition for continuity. Remember, I think, do I ask that next? Oh, I do, okay. But the definition for continuity is a two-sided limit that exists, but does equal, so not equals, it does equal the value of the function. So in this case, it's asking for a point where the two-sided limit exists, but it doesn't equal, so it fails continuity. Well, what does it mean when the two-sided limit exists? That means the function from both sides, they approach the same point, right? They look like they're going to the same place. So like here, the function, does this look like it's going to the same place? No. So the two-sided limit does not exist because the limit from the left is approaching like this point. The limit from the right is approaching this point. So it's not here. Let's look at point. Actually, let's just go through multiple choice. So it's not point D. We just tried point D, right? Let's go start from point A. Point A, the two-sided limit. Does it look like it's going to the same point? It actually does. Cool. So the two-sided limit exists. But does it not equal the value of the function? It actually does equal the value of the function. The value of the function is right there, and it's exactly where the limits are going. So this is continuous. So it's not this one, right? Because this is asking for something that's not continuous. Let's look at B. Does the two-sided limit exist first? Yeah, it looks like it, because the limit from both sides, it's approaching the same point. It's approaching this point right here, right? Now, does this limit equal the value of the function? Well, we plug in B and we get, oh, the value of the function is way up here. That's like, I think, a removable discontinuity, right? So it doesn't equal that. So that's the right answer, B. Cool. Yeah. So that is B. The graph of the function is shown above. What is f? I think I changed the values for this problem slightly for some of them. The graph of a function f is shown above. What is f of -4? Well, f of -4 is, so we go to -4, right? -4 is right here, and we actually plug it in, and we notice that the hole is filled here. So it's going to be 3, right? It's not going to be here because the hole is empty, even though both the function arrives at -4, but the actual value is at 3, right? It's over here. The limit of f of x as x approaches -1. Okay, well, it's just asking us for the straight up limit. So the two-sided limit better exists, right? Okay, cool. It does seem like it's existing at -1. They're both going to the same point. So that point is 4. It's going to be 4. Is f of x continuous at x equals 2? We can already do our whatever casual definition test. I clearly have to make a big jump, so that's clearly not continuous. No. And if we want to look at the limit definition of continuity, right, which I will rewrite, the limit as x approaches a of f of x is equal to f of a, right? So this is saying that the two-sided limit must exist, right? As x approaches, in this case, 2, well, does the limit approaching this point, approaching 2 from the left and right, are they equal to each other? Clearly not. This one's going to 5. This one's going to -1, right? This one's going to, yeah, so clearly no. So with our official definition, it doesn't work either. Is f of x continuous at -1? Well, this one, casual definition, yep, you can clearly kind of tell. Let's look at our official definition. You approach from the left, cool. You approach from the right, cool. So it meets this first criteria, right? It's going to the same point. But does it also equal the value of the function? When we plug in -1, it's also that point. So they're all equal to each other, so yes. Also, remember, it fulfills this criteria as well. Is f of x continuous over the interval of 2 to 4? I don't think I changed this problem. Honestly, this one's kind of, I'm not sure if it's dumb, but I think the answer is, right, because, okay, so first thing I noticed here is that these are parentheses, right? Not brackets. It's not bracketed. Bracketed means inclusive, so I'm actually not sure if this would matter, but since it's not inclusive of the endpoints, right? So the endpoints aren't included, which is good because the endpoints here are holes, right? So that would be bad for continuity. We do not like holes in continuity. We want to be able to just draw it without picking up our pen, right? So that means no holes. I can't even do this. Like pick it up for a second and continue drawing and have a hole here. That's not allowed. So this, without the endpoints, I draw it. Yeah, 2 to 4 works. So I would say, yeah. Write down the formal definition for continuity. Well, I just did it. So remember, it's the two-sided limit that approaches a point. So the limit as x approaches a of f of x. Remember, this is automatically implying the two-sided limit. If I want to be more precise, I can say the limit as x approaches a from the left of f of x must equal the limit as x approaches a from the right of f of x. And that equals f of a and f of a. Remember, for a limit to exist, the two-sided limit must be, like, they must equal the same point. They must go to the same point. So this, like, implies this. If this exists, then the limit from the left and the right must be true. They must be equal to each other. So it's like we kind of shorthand it. We don't even draw it out like this, even though I think it makes more sense. We just combine those two into this. This is the formal definition for continuity. So the two-sided limit must equal the actual value of the function. Yeah. So yeah, hopefully that makes sense. I think we did a bunch of limit problems here, like continuity problems here. So hopefully that makes sense. Is a function f of x, this piecewise function, continuous at the point at x equals 1? Justify your reasoning using the formal limit definition of continuity. Well, let's test x equals 1. So the limit as x approaches, it used to be a, now we replace it with 1 of f of x, must equal f of a, or 1 in this case, right? So what is the limit as x approaches 1 of f of x? Well, so the limit as x approaches 1, so everywhere besides at, so basically what's going on here, in case you're having trouble visualizing this, right? So everywhere besides x equals 1, right? So x equals 1 here. Everywhere besides x equals 1, right? So it's this is, yeah, for every other point besides 1, it's defined by this like parabola. So it'd be look like this, right? Or something like that, right? But at x equals 1, it's some other random point. Now we don't know where this point is. Could be over here. Could be right. Could fill in the hole, right? And fit perfectly. Could be way over here at x equals 1. We don't really know. So that's how we visualize it. But so let's just say the limit of f of x as x approaches 1. Well, just saying intuitively, I already know that's going to be true, right? Because we already drew this function everywhere from x equals, like besides x equals 1. So I know from the left and the right, they're coming to the same point. But let's just test it out. So the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the right of f of x is equal to f of 1. So the limit as x approaches 1 from the left. Well, that's still this function. So let's just plug in 1. So it's going to be 1 squared. So 1 squared plus 3 times 1 plus 5. So that's 1 plus 3 plus 5. So that's what, 9. And then from the right, well, I'm using the same function, right? Because from the right, I'm going to be still in this x not equals 1 domain. So I'm coming from the right. It's coming to the same point. I'm going to use the same equation, 1 squared plus 3, 1 plus 5. So it's the same idea, right? Like from the left and the right, it's coming to the same point because we're all using this function. Cool. Hopefully that makes sense. Now, the real question is, where is this hole, right? We have this parabola, cool, but where is the hole at 1? Like, where does it actually equal to? Well, let's plug in 1 into 6x plus 3. So 6 times 1 plus 3. Oh, that also equals 9. Awesome. So they all equal each other. That means it perfectly fills in the hole right here. So it is continuous. Yes, continuous. Because they all equal each other. Okay, the function g of x is equal to that piecewise function is not continuous at 2. So already told it's not continuous. So it already fails this. It fails that criteria. So we need to know why. Well, let's see. We can kind of try to figure it out ourselves before we even look at the answer choices, or we can just look at the answer choices. So I'm going to try to solve it without looking at the answer choices. I haven't even done this problem. So let's see if the two-sided limit is the same. So approaching from the left, it's 3x minus 7, right? So the limit, so x approaches 2 from the left, it's going to be, because this is from the left, right? Because that's the x negative less than 2 domain. Let's plug it in. So it's going to be 3 times 2 minus 7 is equal to 6 minus 7, so it's equal to negative 1. Well, let's try it from the right. This approaches 2 from the right. That's going to be 2 minus 3, right? So it's equal to negative 1. Okay, the limit from the left and the right are the same. Cool. Now, let's see if it actually equals the value of the function, right? Because that's the second part. So we fulfilled this first part. Cool, the two-sided limit exists, but does it equal f of a? So f of 2, right? F of the actual point, well, at x equals 2, it's equal to negative 5. Okay, so Well, that clearly doesn't match. -5 doesn't equal -1. So the issue is that the two-sided limit looks like the two-sided limit, which we found exists, which is cool, does not equal g of 2. It doesn't equal the actual point. This is g of 2, not f of 2. So yeah, it's this answer choice. Because let's just eliminate the other answer choices too. So g of 2 is not defined. Well, is that true? No, we're told that 2 is equal to -5. So it is defined. The limit of g of x does not exist. Well, it does exist because these 2 points go to the same point. If they went to different points, if this was like -2 or like even -100, then it's going to be does not exist, right? Because they go to different points, but they do go to the same point. So we're all good there. So it's not this. G of 2 does not equal -5. Well, it does because that's a weird answer choice. And we just plugged in G of 2 and it tells us straight up that it's equal to -5. All of the above. Well, clearly it's not all of the above. We eliminated a lot of the answer choices, so it's C. Okay, now, in order to apply intermediate value theorem, a requirement is that the function must be differentiable, continuous, increasing, decreasing. This should be like instant. So intermediate value theorem, the next problem will kind of refresh your memory on what that really is if you forget, but the answer here is continuous. Remember, it has to be continuous for intermediate value theorem to apply. Now, an oven has just been used to bake a cake at 250 degrees Fahrenheit. 1 hour after use, the oven has cooled down to 70 degrees Fahrenheit. Was the oven at one point exactly 72 degrees Fahrenheit in the past hour? Well, we kind of went over this thought experiment in class, right? So we have a really hot oven and then it cools down to a cold temperature. Well, how about the in-between temperatures? Like, is the oven allowed to skip over a temperature? Like it goes from 250 and it's like, you know what, I'm gonna skip 249. I'm gonna go straight to 248. Is that possible? Well, in the real world and in continuous functions, that's not possible. So it's simply not possible. Maybe it cools down really fast, right? It goes from 250 to 248, like in an instant. But still, there was that like 1 microsecond where it was exactly 249 degrees because it can't just skip over temperatures. So yes, it was at one point exactly 72 degrees. So that's the whole idea of intermediate value theorem. I'm just going to reinforce that. So intermediate value theorem, it's saying like, let's say I have a function, right, from A to B, right, and it goes from, let's say like 5 to 2, right? So it goes from 5 to 2, right? Or yeah. Let's say it's just, let's use the oven example. It's cooling down from 250 to 70, right? That means when I connect these 2 points, if it's continuous from A to B, I have to touch every point in between 250 and 70. There's no way to avoid it. So in this case, 72 degrees, it's in between 250 and 70. So there's no way to avoid it. I can try to avoid it. I can be like, okay, I'm gonna go way up over here, like, and then go down. Oh wait, oh no. You see, I still hit 72, which would be like over here or something. There's absolutely no way to avoid it. So that's intermediate value theorem, is like if it's a continuous function between like from A to B, between f of A and f of B, every value is met. So this would be like f of A, because when you plug in A, it's at 250 degrees. F of B is here. When you, at the end, it's 70 degrees, right? So plug in B, I get 70. But every point between f of A and f of B must be met. So hopefully that makes sense. Okay. Last 2 questions. Selected values of a continuous function are shown in the table below. Which of the following statements must be true? Okay, so this, I think I had to stare at this for like 15 seconds just to like understand what the heck I was looking at. But so x, we're told x values, so 1, 2, and 3. So we're basically told, like on this chart, we're given like 1, 2, and 3. We're also told what each of these values are equal to. So we're also given like what the f of x values are equal to. So what they correspond to, f of x. At 1, it's at equal to 2. So it's equal to 2. At 2, it's equal to 5. This is very off, right? At 3, it's equal to 10. Okay, I'm gonna just make this longer just so it's slightly more realistic. So 2, 5, At 3, it's like at 10, right? Over here. Cool. And it's a continuous function. That's very important. Remember, for intermediate value theorem, we have to understand first that it's a continuous function. That must be a requirement. So we're told that these points, they're all connected. We don't really know how, but they're all connected, right? They're all, and there's no like jump discontinuity, because that would obviously break intermediate value theorem. But they're all connected. So I'm just going to draw that, right? They're all connected. Which of the following statements must be true? Well, does there exist a value c on 1 to 2 such that f of c is equal to 6? Well, from 1 to 2, right, does 6 have to be in the interval? Well, 1 to 2, we're told that it goes from 2 to 5. So we know every number between 2 and 5 must be met. So like if this was asking for 3, does that exist? Then yeah, because it's between 2 and 5 and it's a continuous function. That's what intermediate value theorem says. But this is asking about 6. 6 is not between 2 and 5, so no, that does not have to exist. Okay, number 2. There exists a value c on 2 to 3, right, such that f of c is equal to 6. So now it's asking from 2 to 3. Well, from 2 to 3, it goes from 5 to 10, right? It goes from 5 to 10. Is 6 between 5 and 10? Yeah, it is, and it's a continuous function. So we know 6 must exist. 6, it looks like it's met right here, right? Around there. So that is a check mark. There exists a value on 1 to 3 such that f of c is 1.5. So from 1 to 3, is there a 1.5? Well, it seems like from 1 to 3 goes from 2 to 10. So any number between 2 and 10 is met. So like 9.9 is met, 2.1 is met, 6, 5, 3, whatever, they're all met. But 1.5 is not between 2 and 10, so it is not met. So in this case, it's B, 2 only. Justify your answer below in a complete sentence. Kind of just explain your thoughts for this one. Yeah, actually, I'm not going to look for too much on this one. As long as you clearly understand what you're doing and you get the right answer, then you're all good. Consider the function g of x is equal to 3x squared, blah, 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 piecewise function defined in the interval -2 to 2. Does the function... So basically it's asking, is 0, can we guarantee that 0 exists on this piecewise function? Well, what's the first step we have to do? But can we guarantee it exists from the interval of -2 to 2 on this function? Well, what's our first step? We need to show that it's continuous, right? So how do we show that it's continuous? Remember, show that the function is continuous. Okay, well, we're going to see if it's continuous at -2, right? Because that's where the piecewise function is. So it's a piecewise function. So usually a lot of piecewise functions, like we see, they're like this, right? Well, that's not good because that's clearly not continuous. So we need to prove that that's not going on. So how do we prove that's not going on? Well, let's try our limit definition for continuity. So it's going to be the limit as x approaches a of f of x, well, in this case, g of x is equal to g of a. So that means the limit, I'm going to plug in 2 for a, right? So the limit as x approaches 2, you don't have to do all this work. Like if you can do it intuitively, like I'm like going through every single step, but so the limit as x approaches 2 from the left of g of x must equal the limit as x approaches 2 from the right of g of x. It must equal to g of 2, right? So the limit as x approaches 2 from the left, right? So from the left, shoot, did I even design this problem right? Oof. Oh wait, I'm dumb. Okay, so the piecewise function actually meets at 0, not 2. I don't know where I got 2, so it meets at x equals 0, right? X equals 0. So we're really concerned about whether it's continuous at 0, not 2. So it's 0. Fuck, I wrote 2 again. 0. Okay, so 0 from the left. Well, from the left, we're going to use this domain, so using this function, so it's going to be 3 times 0 squared plus 4, so that's just going to be 4, right? This the 0 cancels out this term. So it's going to be 4. Now from the right, we're going to do 0 from the right. So we're using this function now, right? It's going to be 4 minus 5, 0 squared. Okay, well, cool. That also equals 4. Okay, cool. So this first criteria is met. The limit, yeah, the two-sided limit exists and it's equal to each other. So yeah, the two-sided limit exists. Now it has to equal g of 0. Well, what is g of 0? Oh, cool. G of 0 is this same function, right? Because when x is less than or equal to 0, we use this same exact function. Well, we already know I plugged it in, right? 3 of 0 squared plus 4 is equal to 4. So it's also equal to 4. So that also exists. So we know it's continuous. Awesome. Now we can apply our definition for continuity. I mean, our intermediate value theorem, because we know it's continuous. Well, is g of x equals 0 somewhere in the interval of -2 to 2? Well, here's here's where we can tell we plug in -2 and 2, right? So let's plug in the endpoints, right? So at -2, it's 3 times -2 squared plus 4. So that's 3 times -2 squared, which is 4. So 3 times 4, which is 12, plus 4 is equal to 16, right? So the other one is, let's plug in 2. So 4 minus 5 times 2 squared, right? So 4 minus 5 times 2 squared, which is 4. So it's going to be 4 minus 20. So it's going to be equal to -16. So it goes from -16, it goes from 16 to -16, right? And it's continuous. So if it goes from 16 to -16 and it's continuous, does that mean 0 has to exist? There has to be a 0? Well, yes, because 0 is in between this interval. It's in between 16 and -16. So yes, the answer is yes. Because it's between 16 and -16. If it asks us like 100, does g of x equal 100? Well, possibly. Maybe it goes from, it's not guaranteed though. Maybe it goes from like 16 to -16. It goes way up, reaches 100, and then goes way down, and then hits -16. But that's not guaranteed. What is guaranteed though is that 0, no matter what, is always going to be met. No matter how you draw this function, you always have to hit 0. There's no way to avoid 0. You see 0 is met every time. So yeah, that is the packet. And hopefully, I don't think I took too long on that, but yeah, hopefully you can finish it up quick and I'll upload this as soon as possible.